Am I audible?
Yeah, Dylan.
All right, thanks. So I think we can start in, probably we can wait for another 2 minutes so that all the participants can join by that time. I think we can start, right? So we have reached some 42 participants already. Hi, everyone. My name is Dylan Subramanian. I work as a manager for the energy program WRA India. So I welcome all of you to the webinar. The topic of the webinar is thermal energy storage and its potential in India. So before I get into the discussions or the basic concepts of thermal energy storage, let me talk a bit about the housekeeping rules. So the event will be live streamed on WR India's YouTube channel and recorded for documentation purpose. So all of you will be on mute by default. So participants joining online must keep themselves on mute when not speaking. And I request all of you to please use the Q&A box for queries to the speakers. So our speakers will try to answer some of them during the session, and the moderator may pick a few questions at the end of the discussion and pose it to the speakers as well. So I request all of you to kindly use the chat box option for any sort of technical issues, queries, or comments. And for feedback, I request all of you to please drop a mail to indiaenergy@wra.org. And all our updates, including the webinar details or the future events, everything will be posted on our social media handles, including WR India Twitter handle and WR India's LinkedIn page. So let me start with the agenda. So we will start, we have already started at 3 o'clock. We will have a very short session on the basic concepts of the thermal energy storage, which will be followed by a session by Dr. Deepakar Dikshit, who is from IIT Delhi. He'll be talking about the research and development and academic contribution to the development of thermal energy storage. Then we will have a session on the importance of thermal energy storage in the cooling applications, then which will be done by Safar Ure, who is Managing Director of Environmental Process Systems, followed by a panel discussion wherein both Deepakar Dikshit and Safar Ure will be there, and along with them, Ankit Chanwar, who is the Vice President of Plus Advanced Technologies, and Nitin Goyal, who is the founder of InfiCode, along with our senior project associate, Gautami TS. So she'll be moderating that session. So that will be happening towards the end. And after that, we will have a Q&A session. So let me begin with some very basic concepts of thermal energy storage. So I hope this particular session will help you to understand more about the upcoming sessions, the one which will follow after this session. They'll be using a lot of technical terms and other policy things. So I hope that this particular session will cover all the very basic things that will help you to understand more about this particular webinar. I'll start with a very basic question. What is thermal energy storage? So it is the thermal, it is a temporary storage of energy by heating or cooling a storage medium so that the stored energy can be used later for power generation. It's a very basic concept. In general sense, energy storage comprises intake, storage, and release of energy. That's the same principle that's being used for thermal energy storage as well. And the next important question would be, why is it important? So thermal energy storage has the potential to be an important enabler of increased renewable energy penetration in energy systems by making them more flexible, stable, and cheaper to build and operate. So very recently, you must have noticed that storage has gained a lot of attention globally, mainly because it's a critical enabler to integrate a high share of renewable energy. So that's the main case with thermal energy storage as well, and that's the reason why we have chose thermal energy storage for this particular webinar as well. So where is it used? What are the major applications? So it is being used in industries, district heating and cooling, utility scale, power generation, buildings and cold chain, logistics, etc. So within the thermal energy storage, we have different sub-technologies. We will select them based on the suitability of the applications that we want to employ them. So this is a very broader or generic classification of thermal energy storage. It can be broadly divided into three categories. The first one would be sensible heat storage. Second one is latent heat storage, and the third one is chemical energy storage. So the sensible heat storage is it's the most common type of thermal energy storage, and is the commercially viable thermal energy storage as of now. And it uses the thermal energy. It uses the increase or decrease of the storage medium to store the thermal energy. That's the basic principle of sensible heat storage. And we have liquid storage and solid storage. We have different other classifications as well, but I'm not going in detail. And the next one would be latent heat storage, wherein the heat is being stored as the energy that's being used for the transition of a material from one phase to the other phase. For example, you know that a material would consume a lot of energy to transition from its solid state to liquid state. So that way, this particular technology will make use of that property of a material to store thermal energy. So we have different classifications again here. For example, solid, liquid, gas, etc. And the third one is chemical energy storage, wherein we use chemical reactions or chemical cycles to where heat rejections and heat absorptions happens. So that's how chemical energy storage happens. This is a very broad classification again. And now we will understand what are the important parameters that we need to consider while we discuss about thermal energy storage. So these parameters are very important in the sense that whenever we have a discussion on thermal energy storage, whether it be on the policy matters or the scientific or its applicability, it is very important that the technology that's being discussed showcase these properties on a good scale. For example, energy density. Energy density indicates the maximum amount of energy accumulated per unit volume of the storage unit. So this gives us an idea about the size of the battery that would be required to install for this kind of application that we need. And the second one is round trip efficiency. This is again it's a relation between the input energy and energy retrieved from the storage. Again, gives a relationship between how much energy is being given into the storage medium and how much we are able to retrieve it from the storage. Operating temperature range. So this is the maximum and minimum working temperature of the storage system. So we know that certain industry applications or in other applications as well require a very vast range of operating temperature, a very high temperature. So for those applications, it's important that the technology should have very good operating temperature range. And the range of power. The range of power indicates a rate at which energy can be charged and discharged from the storage system. So range of capacities indicate the quantity of available energy in the storage system after full charge. And the final one is storage period. It is the possible duration each technology can store the whole thermal energy. So this can be on daily basis, monthly basis, and even we have seasonal storages where thermal energy is being stored for seasons. Again, I'm not going in detail. I'm not going to mention the numbers and all, but it talks about the future of the thermal energy storage. The report says that the global market for thermal energy storage could triple in size by 2030. And the investments in thermal energy storage going forward is expected to reach between 13 billion USD and 28 billion USD. That's a kind of investment that we are expecting in this particular space. The molten salt storage, which is again a classification of thermal energy storage, which comes under the sensible heat storage. By 2030, we are expecting 631 gigawatt hour of installed molten salt capacity by online. So this is the kind of future. Future looks very bright for thermal energy storage. We are expecting more sort of installations in across different sectors, not just industries, buildings and district heat and cooling. We will get to see a lot of other thermal energy storage applications in other sectors as well. So with that, I stop here, and I will request Dr. Deepakar Dixit to present his session. And before that, let me tell you a bit about his profile. So Dr. Deepakar Dixit is an associate professor at IIT Delhi with almost 19 years of experience in thermofluid sciences, especially in the design and optimization of energy systems. He has a PhD from the University of Western Australia and postdoctoral research experience at CSIRO, Australia, and Curtin University, Australia. So Dr. Dixit has a track record of publishing around 100 research papers in journals of international reputation and 20 monographs and around 60 referred conference papers, sorry. So over to you, Dr. Deepakar. I will stop sharing my screen so that you can share your presentation from your end.
Thank you. Thank you, Mr. Dillon. So I can share my screen now, right?
Yes, doctor.
So is my screen visible?
Yes, Dr. Deepakar, yeah. Yeah, it's on presentation mode. You can now start your presentation.
So yeah, thank you for inviting me to this webinar. So I think this is one of the right topic to discuss about when we are speaking about energy storage, and more specifically today we are pivoting around thermal energy storage, because when we speak about energy storage, it is more on electrical energy storage, but why thermal energy storage? That can be some sort of doubt which some of the participants may have. So maybe after this webinar, they may have some clarification regarding this. So I reckon most of you are having the basic degree as engineering or physics. So hope you understand the concept of heat and work. So the moot point on which we will be discussing today about thermal energy storage starts from our +1 understanding of this concept of energy, and more specifically concept of energy being classified as low-grade energy, which is being termed through heat, and high-grade energy, which is being termed through work. And then eventually, once we get into it, then we do some courses related to thermodynamics, and then try to understand what is quantity versus quality of energy. There we introduce some more deep understanding of thermodynamics by introducing the second law of thermodynamics. So I'm just trying to hint towards the point, as I was mentioning, why thermal energy storage when we are all speaking about batteries, basically the electrical energy storage concept, why it is that. So maybe through this presentation which I will be having, some of the things will be getting clear. I think the stage has been rightly given by the prior talk by Mr. Dillon, where he has conceptualized about thermal energy storage, and then means what makes us to understand the significance of energy storage in general, and more specifically thermal energy storage in particular. Of course, renewable energy sources like solar energy, wind energy, when we are trying to understand the versatility as well as the variability of those sources and trying to match with the requirement, like the spatial as well as the type of mismatch which we have because of the temporal variation, this energy storage becomes very critical. And there we go for the batteries. So here I will coin a new word. I reckon some of you would have heard about it. It is called thermal battery. When we speak about storage devices, so we have coined a new word who all work in this area of thermal energy storage. It is called thermal battery. Here the same concept of battery, where a system goes through the process of charging and discharging, and then the various terminologies which are generally entangled or associated with any battery concept are again very much relevant for this thermal energy storage device also. So the main concept for which this thermal energy storage will be having its place in this area or in this domain of energy storage is the high temperature thermal energy storage. Today I will be giving some insight on this high temperature thermal energy storage, so as to make it at par with what electrical energy storage does. So generally, when we are speaking about processed energy or high grade energy or work, or sometimes we call it the most processed form of energy. So electricity is one such type of energy. So similarly, if we want to make at par with a low grade energy to have a similar type of salient feature which this high grade energy or electrical energy will have, we have to raise the temperature. So the quality of energy which you get at a high temperature, quality of thermal energy which you get at a high temperature is pretty much similar. I will not say exactly same, pretty much similar to the amount of energy which you can extract from a processed energy or electrical energy. So whenever we are speaking about storing energy in the form of low grade energy, thermal energy, so second law of thermodynamics pretty much governs us to that point where we can store energy at a very high temperature. Now, as an engineer, I think you all will appreciate we all go with quantity, not with quality. So it is better to say what is high thermal energy storage, or what is the range of number in which we are speaking about. So generally the one classification has already been given in the previous presentation. The classification goes with low, intermediate and high temperature thermal energy storage. Say more or less around up to 70 or 80 degrees centigrade, that is low thermal energy storage system, low temperature thermal energy storage system. If I'm speaking something say from 200 to around say 350 degrees centigrade, that is intermediate thermal energy storage system. And if I'm speaking beyond 400 degrees centigrade, everything comes under high temperature thermal energy storage system. So if you can speak of that concept or that idea where you can store the energy at such a high temperature, the quality of energy is also high, and then it can more or less have its significance which is at par with electrical energy storage. And again, in high temperature thermal energy storage, there can be some energy storage which we can think of beyond 1000 degrees centigrade. For example, one of the classification given was for metal type of thermal energy storage device, where the metallic system changes its behavior from one type of phase to another phase within that range of high temperature, and then it can be again termed as ultra high temperature thermal energy storage. So today I will be exemplifying some of those cases where we have done some study on this ultra high temperature thermal energy storage. Now this slide pretty much shows the strategies through which we can integrate a high temperature latent heat thermal energy storage system with a power generating SCO2 based cycle, and at the other side we can again integrate it with thermoionic photovoltaic type of scenario, where again we are extracting the energy at a high temperature and utilizing it for power generation through PV, and at the same time going through this criteria of emitting the electrons at such a high temperature. And again, when I'm speaking about high temperature, it is beyond 1000 degrees centigrade. Of course, that is the challenge, because if you want to compare it with the electrical energy storage, then this temperature thing is one criteria which will be making it at par with what an electrical system generates. I think in the previous talk, more or less what is charging, what is the storage capacity, and what is discharging, and how the round trip efficiency of any storage is to be defined, that has been classified. And again, if I'm speaking about one way of classifying the thermal energy storage, basically it is on the basis of the storage criteria. So one is the physical storage criteria and another one is the chemical storage criteria. So physical storage criteria, pretty much it involves the utilization of phase change material, where the sensible and the latent heat component of the system comes into picture to store as well as the release of energy by the process of charging and discharging. And when I'm speaking about the chemical energy storage, it is just by virtue of the exothermic and endothermic reaction through which the store as well as the release of energy takes place in that particular type of energy storage system. Okay, so this slide pretty much shows that how a latent heat thermal energy storage system goes through a various process of sensible heating, then latent heating, and then again finally after reaching its T-thirst point of sensible heating, ultimately again it drops down during the energy release period, when again you can say that discharging is happening of that thermal battery, which is under study or taken into consideration. This is pretty much a standard way of understanding how the energy is being stored in a latent heat thermal energy storage system. I think you can see that from our basics of physics, we understand that the heat storage capacity times the change in temperature through which the system will be undergoing, when you are multiplying with the amount of material which it is participating in that particular system, it is called the sensible heat component of that thermal energy storage system. And then comes the part where we are having the latent heat thermal energy storage system. This is the point where we appreciate how by virtue of change of phase without having any impact on the temperature, like more or less the system remains isothermal. In real life condition it does not, but ideally we say that it is maintaining a constant temperature, and by virtue of which whatever amount of energy can be stored or released comes under this latent component. However, there will be various limitations with the materials which is under study. So I think that I will be discussing during the panel discussion. So these are some of the studies which we have conducted at IIT Delhi in terms of understanding how high temperature thermal energy storage system can be a solution. So the first one which we have taken is silicon, which is having a melting point of around 1400 degrees centigrade. So we tried to understand through an analysis based design, can silicon be a solution when we are estimating to store energy at such a high temperature and then utilize it for say supercritical based power cycle using SCO2, or can it be a part of a thermoionic photovoltaic power generation as envisaged in one of the previous slides. So these are some of the typical results which we got when we attempted to compare silicon with sodium nitrate, and we found that there are some anomalies, some peculiar behavior with silicon at such a high temperature. When the phase change happens, it shows. Unlike sodium nitrate, which is also a phase change material, salt bed phase change material, when we are seeing the behavior of silicon, you can see that silicon starts melting from the bottom side in comparison to that of the sodium nitrate, and that is more governed by the type of vortices which is getting generated. For silicon, it is actually anti-clockwise direction vortices, in contrast to that of the sodium nitrate, which is clockwise direction vortices. So the next one will be giving you an idea how this high temperature latent heat thermal energy storage, say if it is silicon, which we are attempting to couple with a supercritical CO2 based Brayton cycle, what are the salient features which we get? Now, if I'm speaking about the beauty of this supercritical based CO2 cycle, these are the values of the critical temperature and critical pressure at which carbon dioxide works. So beyond this temperature and pressure, it becomes a fluid where both the viscosity as well as the density show some peculiar behavior. So unlike other fluids which has some different behavior, this supercritical CO2 is having the property of a gas as well as a liquid in conjunction with each other, where we take the advantage of utilizing it in a way that the density of this supercritical CO2 becomes higher than that of the liquid, and in terms of the viscosity, it becomes lower than that of the gas. And that makes it a versatile or a superior fluid to be employed in for power generation. And the only thing where I want to highlight the significance of this high temperature latent heat thermal energy storage system is the temperature. If we are having the critical temperature to be around 30 degrees centigrade, and if we are coupling it with such a high temperature of say 1400 degrees centigrade, as we saw from the silicon based latent heat thermal energy storage system, then you actually get to have the efficiency which you can't generally get with any Brayton based, any air based power generation cycle. Of course, there are some criteria like the split ratio which is to be respected when you are designing this type of fluid circuitry for power generation. I think this I will be skipping. This gives a bit of more idea about the nitty-gritty of this thermal battery, which we can design by utilizing PCM, silicon-based PCM, and how this concept has been evolved, and what were the anomalies in the previous model which we have introduced after doing some fine-tuning in terms of the conductive resistance as well as the convective resistance, which each phase change material, when subjected to some change in heat flux, undergoes. I think I will just skip it. These are some of the contours which will be giving you an idea how this silicon-based thermal energy storage system will be storing the energy and releasing it over a period of time. Okay, this is one interesting fact. So generally, when we are speaking about thermal energy storage, or when we are speaking about any system which is actually undergoing a kind of thermal response, we play with the thermal conductivity as well as the heat storage capacity. And there can be various ways, like active means through which we can enhance the performance of that thermal battery, and some passive means. So always active means like introduction of fins or many other physical features will not be a very conducive or means a pocket friendly solution. So sometimes we go for some passive means. Passive means like changing the orientation in which the battery is alienated, or the way you can change the eccentricity of the pipe through which the fluid is flowing. So in that way, you can see that this passive means sometimes create a better option of providing more capacity of storing and releasing the energy from this PCM based thermal battery when we are comparing it with some active means by introducing fins, which is actually not pocket friendly, because you have to intervene by utilizing some technology to make it more efficient. So these are some of the characterization of the phase change material which we have developed over here at IIT Delhi. So and this is one of the experimental setup to show that how this high temperature thermal energy storage system, here we have used solar salt, and how it can be utilized to disseminate as well as to store energy at such a high temperature in comparison to that of say low or medium temperature thermal energy storage system. The last one which I want to highlight over here is that, and when we are comparing a thermal battery with an electrical battery. Say here the comparison it is with 1865 lithium ion battery, and the thing is, the main point which is kept in mind is the amount of energy which is to be stored in the battery, thermal battery as well as the electrical battery. They were kept constant. The beauty of this thermal energy storage battery is that the energy density in terms of the gravimetric as well as the volumetric energy density is much higher in comparison to that of the lithium ion battery, which we have taken into consideration. This was just to make some apple to apple sort of comparison. Of course, the catch is you have to maintain the temperature at such a high temperature, which I'm speaking about, say around beyond something 500 degrees centigrade, or at most to the melting point of the metal, which is taken into consideration for designing this type of thermal battery. This is the concept of thermoionic photovoltaic, which also can utilize silicon as one of the thermal energy storage system, and has the potential to store high temperature heat, and at the same time help us to produce the electricity with an efficient module, which unlikely we will not be getting at some low temperature thermal energy storage system. So to sensitize you, like, it is not just a myth. The examples which I have given, there are certain systems which has been developed.
Excuse me, sir. Sorry to interfere. Very interesting, but I request you to be please mindful of the time. If you can.
Sure. I think
yeah.
I'm done. I'm done
Okay,
with the presentation, more or less. So I think this was also covered by you during the previous one. So I think whatever I have spoken till now has been jotted down in this conclusive slide. So yeah, these are the publications. These are the references. Thank you for your attention.
Yeah, thank you so much, sir. This is very interesting. Unfortunately, we didn't have.
No. I'm done.
Time to. Okay, all right. Thank you so much.
So I will pause my sheet.
Yeah.
I have paused.
I'm not sure if we have questions posted on Q&A, but we'll come back to you if we have.
Sure.
Okay, definitely. So, sir, can I request you to please stop sharing your screen so that I can share my screen? And,
yeah, I think I have done a resume share, but I don't know, it's not allowing me or something. And show. And I have stopped sharing, I reckon. It is showing resume share. Can you please check?
Okay, let me try the other way. So can you all see my screen?
Yeah, I can see your screen.
Oh, all right. Thank you so much. So it's time for us to move to the next session. So the next session, I again thank you, Deepakar sir, for giving us insights on the theoretical side of the thermal energy storage. It was very exciting to recollect all those good memories that we had during our college days as well. So I'll come back to you during the panel discussion. So now it's time to go to Mr. Safar Ure. Safar, Mr. Ure started his career in 1981 as a mechanical engineer. And since then, he served in a number of companies like Carbogas in Turkey, JNE, Hall in UK, in the refrigeration, mainly in the refrigeration field. Also, Mr. Ure used to be the chairman of SIPSE Thermal Storage Group in the UK. Mr. Ure is the founder and managing director of the PCM Products Limited, specialized in PCM-based thermal energy storage products and associated low energy cooling / heating technology. Currently, he's the managing director of the environmental process systems. So, Safar, can you hear me?
Yes, if I can write the button. Yeah, I can hear you.
All right. So I will stop sharing my screen. If you have a presentation, you can please share it from your side, and over to you.
I'll try to. Well, it says you cannot start screen share while the other parts. Okay, you have to come out of sharing.
I stop sharing it now.
Okay.
Okay.
Can you see my screen?
It's loading.
Okay.
Yes.
It's a long way, India from UK. It'll take time to get there. Right. Is all there, is it?
Yes, over to you.
Okay, I suppose it's good afternoon to you all. And I'll be talking about the thermal energy storage, but rather than theoretical in side, and I'll be talking about the practical, is the real world, where the application. And here is basically the built environment. We are talking about basically where the people live. And if you look at the top, that blue backgrounds, and there's a building, within that building, we need to provide services, what we call it M&E, and also P as well, the plumbing. So therefore, they need lights, power, heating, cooling, and hot water. And these are the essential services in a modern life. And how do we do that? Using various basically secondary energy sources like boilers, chillers, heat pumps, or you name it, whatever the basic machinery to provide these services. And in order to run these, we have a primary energy input, which mainly the fuel, either gas or oil. Or, of course, you need to provide water and electricity. So those are the step-by-step building blocks of modern life, what we call it. And lately, we start adding some sort of passive cooling, free cooling, as well as solar in the means of either thermal or electric to top it up and try to minimize the impact and use of these primary energy fuels. What is a thermal storage? And I think it's already been described at the beginning, but storing high or low, what basically the arbitrary, what I decided what is high, high means about 0 degrees C, the water ice, and low below the water ice, 0 degrees C, temperature for energy storage for later use. And all it does, it bridges the gap, and you store the energy when it's available and bridge the gap for when is energy needed later date and store that in the form of high or low energy. And there are two types of energy storage available to us. I ignore the thermochemical for the time being because there is no real application as it stands and there is no real manufacturer either. So therefore I keep it simple, sensible, and latent. Those of you who are not familiar, the difference between sensible and latent, the simple description, if you take a cold water out of the fridge, put in a glass and leave it in the room, and it will very quickly get warm and reach to the room temperature, and that's the sensible. But if you put a couple of ice cubes into the same glass, it will get warm until the ice temperatures around 0 start melting. It will keep the drink cold until the ice runs out. And that's the basically latent heat, that ice energy keeping the solution cold. And that's, but of course, you need, at the first place, you need to put awful lot of energy to make ice. And once that energy is stored in the ice format, it comes back on the way back. And that's the difference between sensible and latent. And here is the typical sensible storage applications. Really, if you are trying to store chilled water, you need huge buckets for industrial application. Or most of our domestic house, we have one of these hot water tanks. And it's purely relying on specific heat and the temperature difference of the solution to store the heat. One of the disadvantages, because specific heat is of water, let's say 4, and therefore you need huge volumes to store the same amount of energy. One way to reduce that volume requirement, going to the ice storage. Ice storage could be dynamic or static, well-known, well-established. And I use this in my, while I was wearing a short trousers, and it's a very well-established, universally available water technology. But unfortunately, the water ice, one of the application is air conditioning, and it is basically the period is 0 degrees C. It limits what you can do with it. And if you want to move away from 0 degrees C ice, you need to deal with chemicals and what is called generally the eutectic materials or phase change materials. And they are really, in principle, mixture of various chemicals to provide you an ice different than 0 degrees C. There are two common products available which commercially use. Salt-based products basically is the water is the working media, but putting different salts, like for example, the table salt you put into your meal, if you put 20% into the water, it freezes around minus 22 degrees C. But if you put some salts like Grober salts or calcium chloride, instead of that freezing temperature of the water going down, it goes up all the way to the 117 degrees C. So therefore, the salt-based products, the working media is water, and the salt within that water alters the freezing temperature. And therefore, as far as the hydrated salts are concerned, salt-based products, pretty natural, stable, but nevertheless, you need to be careful how you handle the chemicals in terms of temperature and the pressure. And that's one option, hydrogen and water compounds. The other one is the hydrogen and carbon compounds of organics. That could be simple paraffin, waxes, vegetable oil, soya, even the chocolate we ate and the butter you spread onto your bread is a PCM, but very low latent heat. And here there is no water. It's hydrogen and carbon chains. And unfortunately, of course, the fuel you put into your car and as well as you burn on your cooker is also hydrocarbon. So therefore, you have to be careful how you handle hydrocarbons on the fire aspect of it. But nevertheless, those are the two common products commercially available, what you can do in terms of thermal storage. Here is the range all the way from -100 all the way up to 1,200. Metals are wonderful PCMs like aluminium, iron. That's a perfect PCMs, but very, very high temperature. Molten salts, those are rocks basically melt and becomes basically anywhere between 90 to 885 degrees C range. Hydrated salt, again, as I mentioned here, water-based, and we alter the freezing temperature of the water between 7 and 117. Organics, like paraffin waxes, between 1 degree C, 167, and in fact, 167 is a sugar, you can eat it. Solids, these are the new additions, polyglycol-based materials, again, organic, 25 to 180 degrees C. As I said, the high and low, the benchmark is water 0. Below it, what we call it, the eutectics. Again, these are water-based with different salts between -74 to 0 degrees C, and also alcohol-based, organic, -100 to -22. So this is basically it. These are the basically commercially available, what we call it, phase change materials, ice different than 0. Now we have the materials, what we can do, what we are using for the thermal storage, but also the question is, why do we need thermal storage? The first, if you like, the benefits of thermal storage, instead of climbing this mountain, and this is the cooling load of a typical building, or this is the heating load of a typical building, you know, very big buildings, heating load in the morning and late in the afternoon when the people come back, and the air conditioning, you have a lunchtime, the peak. So you have these mountains to climb. Instead of climbing these mountains, if we shift basically those peaks to the off-peak periods, and we can level the load, and that means we need a smaller machinery. So that's the first advantage thermal storage offers us, whether it's all heating and cooling duties. Second one basically is the running cost reduction. The reason is, this is a typical Indian electricity generation over 24 hours. You can see nuclear, solar, hydro, and all the rest. But nevertheless, bulk of your fuel cost, energy cost, comes from the coal. Burning the coal basically is in India. And you can see, here's the blue line, and that's your electricity price. It's not fixed, although you may be paying fixed, but on the grid, it's not fixed. It fluctuates and change every hour. Look at 3 in the morning, and look at basically the 7 in the evening, the energy prices. And that basically is also the following exactly the electricity consumption. The higher the consumption, higher the basically the utility companies charging you the load. So if we run our heating or cooling instead of here, and if we run there, and we will be saving almost 20–30% of our running cost. So therefore, following the electricity prices and run the machinery when the utility cost is less, it will make a lot of economic sense. And in fact, if you are spending money for the thermal storage, it will pay back. So therefore, that makes it very attractive investment. And also you're helping the grid, reducing that mountain peak they have to produce. That means less power plant. And another big advantage now coming more and more, and India will be following the same, wind and solar. And sometimes you have a very huge, this at the moment, very little, this yellow solar, but in the future it will be big, and you will have the wind. And therefore, when this energy available, also we can store in terms of reducing the peak, the need for electric production from the thermal plants like coal. And the third hidden benefits of, if you like, thermal storage, reduction in CO2. And here is basically the Indian generation profile. 52% comes from the coal, hydro 13, which remain more or less the same. You won't be able to building a lot of dams. Wind likely to go up and solar likely to go up in the future to reduce your CO2 emission. But nevertheless, as you can see, the mix of this energy generation here, and that is the up to 2027, what they expect the India to be. Again, you will be having basically 44%, almost half of it comes from the renewable. Only renewable solar, PV, as well as the wind. And therefore, really is that means is the cost of this CO2 emission is next to nothing. And here is, I don't have the Indian breakdown as like this, but here is the UK. And look at that very interesting concept of CO2 reduction. Here is the production of electricity in the UK. And you can see we have the nuclear is the base because it has to run all the time. And we have gas turbines. It's mainly we use a lot of gas. Wind and solar taps up, but is unpredictable. So therefore you need the main machinery to provide. And here's biomass coal is very little because of the CO2. But look at the CO2 overall emission from per kilowatt hours electricity. During daytime, 0.339, nighttime is 50% less. So not only also the price of the energy is here high when the CO2 emissions high, but also of course off-peak periods, CO2 emission is less than in comparison peak. By using the main power, if you like, the bulk of it off-peak periods, we are not only saving money, but also we are saving a lot of CO2 using exactly the same kilowatt of our electricity. Hence the hidden benefits of the thermal storage, significant reduction on CO2 emission related to the power generation. And here is the basic typical building again, where we can apply the thermal storage all the way from heat recovery from these cooling towers or the rejection from the cooling machinery, and some solar wasted from the machinery is what we use, like CHP absorption chillers. And we can also shift the load on the chill water system for cooling. So those are the really is a lot of range. The phase change material offers us, and between like 13 to almost 8,500 degrees C levels, it offers a lot of benefits and opportunities to shift the loads and level the loads on heating, cooling demands. And that really, the conclusion of that, really, having a thermal storage and ice different than 0 degrees C, it offers us utilize the free energy. What's free? The cold night and warm day. If we can bring the warm day to night, we reduce the heating. If we bring the cold night to day, we reduce cooling demands. If we can get away with totally free is great, but not like in life is everything is free. So we have to use and waste and spend something. And if you are going to use any machinery like heat pumps, always look at the way where we can basically minimize the waste. And if we are producing cold, that means we are dumping some lots of heat, or vice versa. If we are producing heat, we are extracting energy and making cold. So can we use that? And the PCM type, different than 0 degrees C thermal storage, it enables us to store when is available that waste heat or cold, and use later when we need the cold and heat. Load shifting leveling is critical because the grid cannot cope. There are peak demands. You need awful lot of plants to satisfy that. And therefore, by shifting and leveling the load, rather than climbing mountains, we also help the grid and leveling and running steady. And of course, it also enables us to store the free energy available like solar and wind. Mix and match technology is very important rather than one. And you can mix and match technology and get the optimum solution to achieve that. And one basic, the most important things here, to never forget the return on investment. Someone has to pay for this idea. So today, unfortunately, every single company run by accountants and shareholders. So therefore, they want some return. Anything beyond 4 years payback, you will be wasting your time commercially. Nobody's interested in. And therefore, whatever the money we are spending to achieve all of these has to come back within a few years. And another most important thing, always use the right technology for the right application, not for the sake of applying a technology if it's not suitable. I came across a lot of those applications, which really is the money wasted and achieve nothing. And because probably the client asked combined heat and power or absorption or solar or PV, whatever they did, but in fact, it was the wrong application and money wasted, never returned. That's it. And I hope I managed to give you a few idea what is available in real world, what the products out there and the technology been applied. And if you have any questions, I'll be more than happy to clarify. And if anybody else needs further information, application example, just drop me an email. Thank you.
Yeah, thanks. Thanks, Zafar, for that. Very interesting. It's nice that you have considered a presentation of, you have included slides that are very much relevant for the India context, and you explained how thermal energy storage can effectively be used to use for optimizing the demand. So we will definitely see if we have questions, follow-up questions on the session that you had. And now we will have to move on to the panel discussion. Let me share my screen. So, as I mentioned, in the panel discussion, Dr. Dibakar will be joining, plus Dr. Zafar will be joining, and along with we have Dr. Nitin Goyal. So Nitin is the Chief Executive Officer of Inficold. He has over 20 plus years of experience with more than 15 patents in solar and cooling. He's a graduate from IIT Bombay and PhD from University of Florida in solar refrigeration. He has earlier worked in the field of electronics cooling for laptops, solar absorption and thermoelectric refrigeration systems, etc. He has licensed cooling technologies to Godrej, Whirlpool, Lloyd and Oasis in his previous companies. So I welcome Nitin to the panel discussion. And then we have Ankit Janwar, who is the Vice President of Plus Advanced Technologies. Again, Ankit Janwar is an IIT Roorkee graduate in Polymer Science and Technologies with more than 10 years of experience in successfully commercializing innovations across sectors using the phase change material technology. He has completed CFA Level 2 and has also done short business courses from London School of Economics and Political Science and Stanford Graduate School of Business. He was also part of the Champions of Change group formed by Niti Aayog, Government of India, to present ideas on transforming India by 2022 to the Prime Minister of India. He was also recognized as Work Hard Technology Activist of the year 2017 and was among the top 5 innovators under the FICCI DST Lockheed Martin India Innovation Growth Program. I welcome you, Ankit, to the panel discussion. And finally, T.S. Gaudami, she's working as a senior project associate with WRA India's energy program. So Gaudami is a senior project associate at WRA India. She is mainly focusing on enabling ecosystem for MSMEs to adopt low carbon energy transition pathways through policy interventions, stakeholder engagement, innovation, and technology adoption. In the past, she was engaged with small-scale businesses aimed to generate sustainable economic growth, employment, and livelihood opportunities while prioritizing the environmental harmony. So Gaudami will be moderating the session. So I hand this over to you, Gaudami. Please take it further from here.
Yeah, thanks, Dylan. Good afternoon, everyone, and welcome to today's panel discussion on opportunities and challenges of mainstreaming thermal energy storage in India. To begin our discussion, I would like to ask our first question to Dr. Nitin. So what are the opportunities and challenges of thermal energy storage for large-scale applications in India? Dr. Nitin, over to you.
Yeah, hello. Thanks for, first of all, thanks for inviting me in this panel discussion. See, one of the main advantage I would say for thermal energy storage, right? And I'm very specifically talking about cooling, as our company have expertise in providing cooling with thermal energy storage. So the advantages over your lithium ion or lead acid batteries are over very high discharge rates. That is one. Second is I call these batteries like a so we have these hybrid cars where there's a engine and motor, and both of them are working in tandem. Same thing happens with these ICE batteries. So if you talk about, let's say you have a Burj Khalifa which is doing ICE cooling for air conditioning. So a compressor along with ICE battery are working in tandem like a hybrid car to provide cooling. And with that, your compressor becomes small. We can store cooling, and we can also ride along the peak power differential tariffs. So all of these mix results into opportunities which are quite large in size. This is one. Second is no degradation, right? So lithium ion degrades within 3-4 years. Here no degradation, no chances of fire, no chemical recycling issues. And apart from that, the price, I would say the initial capital price is 1/3 of electrical batteries, and the life cycle is more than 10 years. So we are talking about 1/30th of the life cycle cost. And then there are few applications which no one can meet. Transit, right? So like Plus Polymer is a market leader in providing these gel packs. That is another, right, one kind of a concept where no battery can provide cooling, right? So then so the work which we do for very instantaneous cooling of milk or very high pre-cooling road, those are the another opportunities. If we summarize these opportunities, off-grid solar integration is one where we can integrate off-grid solar with specifically for cold storages. Second is 80% of commercial load is air conditioning. Those can be also integrated with TES. Third is incentive on feed-in tariff is going down, and we can use these energy storage concepts to store solar for captive usage. So I think I have mostly I have summarized most of them.
Yes. To build on that point, Mr. Ankit, can you please bring to light the HVAC systems in residential buildings?
Thank you, Gautami, for the question. And thank you for inviting me. Especially with respect to the HVAC system in residential buildings, I think traditionally, or in commercial buildings, traditionally what has been used in India is the ice storage systems. Now, and historically, I think one of the companies which pioneered the ice storage system in India was Crystopia. But see, HVAC is very capex driven, a long-term project, and the implementation, unfortunately, post has not been up to the mark. And therefore, the adoption of ICE, which is essentially also a thermal energy storage or a phase change material, has not scaled up in India like it has in other international geographies. Also, I mean, in India, we generally look at the upfront cost and not look at the total cost of ownership. So that has also been the challenge because we don't have appropriate financing models to fund such big projects. We at Plus have done PCM-based phase change or the phase change material-based HVAC systems through partners in Ireland and in other parts of Europe, which are much more efficient than the traditional ice storage systems, which have a longer payback, which have an initial capex investment much higher. But it is successful in Europe only because they look at that long-term, total cost of ownership, long-term payback, but also because those economies have those financing options available to fund such capex, that money is available. I think purely from India perspective, we're still lagging behind in terms of HVAC. While the phase change material and the thermal energy storage awareness has increased dramatically in the last 10 years, especially in the last 2-3 years, but adoption, especially for HVAC systems, are still very low. And we do receive a lot of requests across, industry segments, but I think the number of requests for ice storage, partly because of, I would say, poor implementation in the last decade or so, by it has got a bad name in itself. And but the high capex, the whole financing around it, the longer payback of more than 4 years, 5 years, that kind of appetite, I would say, is not there in the Indian market right now. However, that adoption is increasing in international markets.
Okay. Okay, to build on that point, Mr. Zafar, can you please throw some light on deploying thermal energy storage in the building sectors with the global viewpoints?
Yes, sure. I think this is the main obstacle for any thermal storage, and you will be adding something extra to a conventional system, what people know, what people apply. So if you basically introduce something new or addition, and quite often it adds a cost. And that cost, as I said, has to be justified in terms of return and benefits for the client and application. One of the biggest problems, especially on the going to the phase change material, you are dealing with chemicals. And when you are dealing with buildings, you are talking about tons and tons of material. Even if it's, 1 rupee a ton, and when you put 500 ton, that still adds a lot of money onto the cost. And therefore, to find the benefits of cost versus benefits has to be justified. That's one of the main obstacles. But the circumstance is changing, and the energy prices and the oil and gas prices is all over the place, and the renewables are catching up. And India is also catching up pretty fast with the solar, especially, and the wind probably will follow. And therefore, once we get that sort of unpredictable energy supply source, by nature, by basically the force by the environmental, if you like, the pressures, you will have no choice to have some sort of thermal storage somewhere along the line, or store batteries. Batteries at the moment not practical. The reason is not practical is the life of the batteries. And that really makes them uneconomical for the use of a 20-25 years operation. You will end up replacing every 5-10 years. And the PCM is a static system, or the thermal storage, and therefore the life is not an issue. And therefore, overall, in the long term, thermal storage will be better or economical, attractive in comparison with the batteries. But as I said, the main problem to find the application, cost versus benefits can be justified, and applications. So far as I know, the biggest applications in India is use of the phase change material is the telecommunication, these mobile towers using passive cooling. And that is probably the biggest. Apart from that, I'm not aware of any large scale building thermal storage applications. Again, the reason probably most likely cost, and not having a local manufacturers. We have installed phase change material base thermal storage systems, large installation, the train stations, airports, and up to 15 megawatt hours. And certain applications like train and air stations and airports, generally you have almost 6-7 hours off peak, not in use, is nobody using the airports, for example, midnight to 6 in the morning. So you have a massive infrastructure. If you can utilize that or reduce 20-30%, that's a significant saving. And if you use especially phase change material like 8 and 10 degrees C ice, you don't need glycol or sub-zero temperatures and complicated controls. And therefore, really, it makes economic sense. Very quickly get back. And those are the applications always. It's not a magic solution, but it has to be right application with the right technology, and always beyond the technology, looking for the cost versus benefits. And if you achieve any free cooling or free heating, and using that free energy, and using the advantage of having ice different than zero to satisfy the building demand, and either heating or cooling form, it makes economic sense. And certainly it makes environmental sense rather than using fuel. But again, as I said, the challenge is always take the application and work backwards rather than a blank statement. And they are expensive what they do, phase change materials especially, and therefore they have to be used sparingly and cleverly. And if there is a right application and right, if you like, the technology applied, it works as a tree. But as I said, rather than a blank statement, it has to be application taking like humans, individuals, and work backwards. What technology? And also in my presentation, the last item was right technology for the right application and the mixed technology
Yes.
rather than one. And that's basically what I will suggest. Looking in the application, work backwards, what works best, not technically, but economically.
Mr. Zafar, I have one more question for you. So does the absence of effective standardization challenge the scalability of the technology?
To be honest with you, it is one of those technology you could standardize in as much as you can. But as I said, you are dealing with hundreds of different chemicals, technologies, temperatures, and applications. And applications all the way from space stations down to the submarines going 3,000 feet, whatever is below the ocean. So technology is so widely applied and it's very, very difficult to standardization. And in fact, I'm part of a committee on the American Society of Mechanical Engineers. We already wrote the first standards of in the safety aspect of the high temperature PCMs. Now the second committee is basically writing another standards in terms of, if you like, what are the precautions, especially on the high temperature side, and because they are pretty dangerous in terms of the temperature. So there isn't any, the standards you can create to cover the whole range, and it will be individual standards. There is a European list called RAL Setup Organizations, but that's a private one, and you have to pay money and join, and it's not necessarily the serious like Indian Institute of Engineering or ASME or one of those, like the SIBSI type institution. Is a very much private commercial interest. And there isn't any standard at the moment as such we could refer. And because, as I said, applications are so varied and so different, it's not like car. If you are producing car antifreeze, it's obvious the engine is the engine, internal combustion, you can make a standard of it. But this one is so wide application, wide range, wide chemicals, and wide, like a cheese and chalk. Is very, very different. And therefore, I would imagine we will not see a standard of thermal storage or PCM as such. It will be individual sectors, individual technology, writing their own, if you like, the guidelines. But I think as the practical application will dictate what the standard would be.
Yeah. Thank you, Zafar. Thank you very much. So, Professor Dibakar, I have a question for you.
Yeah.
Is the existing technology capable of being deployed for large-scale applications with its current efficiency level?
Sure, yeah, we have. And I think the best application on the cooling side, using 8 or 10 or 13 degrees C phase change materials, because they can be applied as a retrofit to any existing chilled water systems straight away. And therefore, that makes it very, very practical in technical terms. And especially if there's a utility prices, big difference between day and night and off-peak periods. And also another advantage, of course, running the chillers, air conditioning machinery overnight, especially like India, for example, Delhi, you have 45 degrees C day temperature, but night is only 30. So therefore, having that 15, 20 degrees C cooler ambient to run the machine, you automatically save 20, 30% of your electric consumption straight away. And if the electricity prices by half, let's say for argument's sake, using 30% less plus 50% less cost, and you are saving awful lot of money and energy. And therefore that may, if you like, to pay the money you are spending for the phase change material. The other alternatives options is going ice storage, which is cheaper than PCM, but you need awful lot of glycols to add into your system, and awful lot of modification. And by running your glycol chiller -10 to make ice overnight, all the benefits you gain from ambient, lower ambient is lost. And in fact, ice storage consumes more power, electric consumption, than a conventional chiller during daytime. And therefore you are paying more electricity, if you like, consuming. And the only advantage is saving, consuming, the higher energy consumption, but having the utility cost is less. And depending on how much money you can save to pay for the ice storage. So the ice storage is an option, wonderful technology, nothing wrong with it, but economically sometimes difficult to justify because of that loss energy efficiency from the lower ambient. You are losing going glycol, but it's a technology. That's probably one sector in India will be growing a lot. You will be growing a lot because you would need cooling anyway in India all the way, and dehumidification like Mumbai and all the other coastal areas. Heating is another one. In the northern part of India, you need heating, especially on the mountains with some pieces. The best application could be using underfloor heating with 27 degrees C, 30 degrees C PCM, and using solar collectors. So therefore, you might be able to do a lot of heating using free solar energy, using solar thermal collectors, especially if it's a parabolic concentrated collectors. You will produce 35, 40 degrees C water even in the middle of winter. And that basically does your heating, and therefore that will reduce your demand for coal or any other gas and heating demand. So really, those are the two sectors economically and the beneficially for the Indian applications, getting free heating as much as you can northern part of India, and free cooling using solar. Again, we did that Qatar stadium cooling, for example, using sun to produce hot oil from the parabolic collectors and run the absorption chillers, thermally driven chillers, and freeze the 13 degrees C PCM all day long when the sun is available, and cool the stadium for 3 hours overnight. And that is technically possible. And there are certain applications, for example, you might be able to use solar cooling as best as you can, but also, of course, using the free cooling, utilizing the benefits of cool nights and store that cool energy and try to reduce the peak demand during the daytime. And that could be really the three sectors I can see in India will be as much as free cooling and the free heating as you can achieve, and also shifting the loads, leveling, if you like, across the board will prepare Indian technology for the future, because future is, whether we like it or not, will be renewable. And I show you those slides, we are talking about that slide 2027 is just only 4 years down the road. And you are talking about 15% increase, renewables, solar and wind. And given another 10 years down the road, that will be almost 60-70%. So therefore, you need thermal storage, whether you like it or not, because both solar and wind is unpredictable. It's there or not. So therefore, you need to capture as much as you can while that free energy is available, store it, and reduce basically the peak periods later. So those are the three technologies: free solar heating, passive cooling, and passive heating using sun, and utilizing the thermal storage for existing, mainly the retrofit for chillers, chill water systems. So those are basically the technologies I would say India will be following.
Yeah. Thank you, Zafar. These are really practical examples from global to India growth. Professor Dibakar, can you please add on to these points, and can you give us a case study?
I think like Zafar has rightly mentioned about like how this can be materialized from technical as well as techno-economic viewpoint. I just want to give some examples of the studies which we have conducted at IIT Delhi. Basically, COVID-19 was one of the eye-opener during which we required a very intensive air change per hour in a closed space to abate any sort of transmission of infection. But at the same time, in countries like India, we require a very high heating, ventilation and air conditioning loads. So this 12 ACH, which has been proposed by ASHRAE, WHO. It was really means biting our pockets when it goes to having such high air change per hour. And there, this type of technologies of intervening the facade using phase change material or any such like passive means can come up as a solution, where we saw that there can be certain reduction in the air change per hour which we can propose. Like the study which we have done was for a small healthcare unit where 2 patients were housed, and then we just saw that can 12 air change per hour can be ACH can be reduced to something optimum. And we found that, of course, it can be reduced for a scenario which we were studying for Delhi to 8 air change ACH to 8 ACH. So that, but of course the envelopes were retrofitted with some phase change material and insulation in those envelopes. So you can see that how an active air conditioning can optimize its energy consumption by utilizing this type of passive features in the envelope. So from 12 we came to 8 air change per hour. So that is one example which I want to give. And as I was showing in my talk, if we want to compare, because I was seeing there were questions regarding what should be the time of storage capacity of this high temperature thermal energy storage system. So if we want to compare what we are having, I don't want to name any electrical energy storage technology. There are n number of them, which at the moment we think that they are superior. But thermal energy storage, if we want to compare, we have to work at a very high temperature. Like as I was mentioning, say beyond 500 degrees centigrade, and if we can take to 1000 plus, that will be the optimum point where we can get the exergetic efficiency of both electrical energy storage system as well as thermal energy storage system at par with each other. Of course, there are limitations, because when we try to scale up things, they don't go in tandem with what we do in the lab. But I showed some of the examples where high temperature thermal energy storage system has been actually showcased as an example where we can store energy at such high temperature and can be utilized for solar thermal power generation, can be utilized for some process related activity, which comes more handy for us when we are trying to compare it with any of the electrical energy storage technology.
Yeah, thank you, Professor. Dr. Nitin, I have a question for you. Yeah. How do you see the current regulatory policy and market design affect the thermal energy storage in Indian market?
Yeah, definitely. So it is not, thermal energy storage is not that glamorous like your lithium-ion batteries. But they do have a very important role in the Indian ecosystem, considering solar is at 2 to 3 rupees, and the only viable option of storing cooling is right now thermal energy storage. And we are seeing day-to-day inquiries from very large corporate houses who wants to solarize their air conditioning. Their corporate headquarters, I will not name them, right, in Bangalore, in Bombay, and everyone is asking for thermal energy storage. So in fact, a lot of solar cooling cold storage companies which were working on lithium-ion batteries, I have now moved to these kind of batteries. In fact, from a regulatory perspective, Ministry of Horticulture Department, they do have 100% subsidy if someone is installing thermal energy storage on a cold storage. So it is very, very well defined. Also, MNRE, the Ministry of Renewable Energy, they only recommend thermal energy storage for solar cold chain application. So these are the two. But this is not enough. We don't have testing standards for solar cold storage or solar milk coolers in India. Another few thing I would recommend is that, and in India there is a lot of pollution happening, right? I would say in top 10, 90% of cities, right? We have India right now. And still, there should be some regulations behind ban DG, and instead of that, we should have thermal energy storage for cooling, because so similarly, like for example, very recently, the state government of Chandigarh has announced, right, no, only lithium-ion scooters. So same thing can happen, that no DG for cooling, right? It has to be ICE energy storage for cooling. So those kind of things are really required still. And then another is this green traceability of perishables. That is missing in India. We are talking about ethical traceability, but what about green and clean traceability of fruits and vegetables?
Okay. Mr. Ankit, can you build on this same question? What are your viewpoints?
Hi, Gautam. Thank you. So, I think in India, especially, regulatory and policy changes have not happened directly, which affects thermal energy storage, but it's more related to industry policy changes and industry regulatory changes, which in effect creates either awareness about or generates interest in the thermal energy storage applications. So for example, one of the changes in the electric vehicle industry generated a lot of interest in phase change materials and the use of phase change materials for passive cooling of lithium-ion batteries. So government had introduced an ASTM standard which talked about thermal runaway and how it becomes an issue and leads to fire incidents. I'm sure many of us would have read about the fire incidents in electric bikes. And suddenly there was a lot of incoming requests to us for phase change materials for cooling of lithium-ion batteries. So it may not have directly said include phase change materials or have a thermal energy storage or it is mandatory, etc. But it is these changes on the sides around the industry which leads to this interest or generation of interest in phase change materials. Another example is the whole vaccine movement, COVID vaccine movement. Suddenly there was awareness about vaccines temperature and the need for maintenance of the temperature during transport to every layman. I mean, everybody was talking about Covishield 228 and XYZ at -20 because it was all there in the newspaper and the government was very keen on ensuring that there was temperature maintenance. Now, the best effective way of maintaining the temperature in transit was the use of phase change materials. So there's an automatic generation of interest. But I think, yeah, there has been no direct policy change which affects us or regulatory framework, but it is these ancillary changes in a particular industry which affects the phase change materials.
Yeah. One more question to you, Ankit. What could be the best business models to attract clients to thermal energy storage?
Good question. And I think one of the business models which has not been tried or which have been tried but not so much at scale is product as a service. See, the phase change materials or the thermal energy storage applications sometimes have a high initial investment, but it has a certain payback after 2 years, 3 years, or 5 years. And the business model which essentially works on giving phase change materials or the thermal energy storage as a service and not selling the product to the industry. So for example, if I say that if you include phase change materials in the reefer trucks will lead to 20% diesel savings, then I don't charge you for the phase change materials, but I charge you for the savings per month. So you pay me that for 3 years. So what it does is that it brings in a lot of confidence to the customer because I'm investing myself. So the customer doesn't need to invest upfront. And there is skin in the game. So immediately that entry barrier in the mind, whether the technology will work or not, there is an initial capex investment, which is higher. that entry barrier is removed. But to enable this, I think what is required, and I think I mentioned this in my previous, is the whole financing options. And because phase change materials and thermal energy storage leads to energy efficiency, a lot of these energy efficiency, ESG related financing options are now available at a much lower interest rate. So I think these kind of business models will become more and more viable in future. So leasing a reefer truck, leasing a cold storage, leasing, for example, a cold chain solution. So why would one need to buy a perfect vacuum insulated panel, phase change material based last mile delivery box for pharmaceutical companies? I can just lease it to them, and because phase change materials have a life for 10 years. So I'm guaranteeing that life. I'm also involved in the system. So the adoption increases. So I think this is one of the business models which will be seen more and more. We are ourselves trying to toy with the idea. We've not done it, but this is becoming more and more viable. And I think this is what will lead to faster adoption in the future.
Yeah. Thank you, Ankit. Dr. Nitin, can you give us some description on this with respect to agriculture sector? Thank you.
Yeah, so our focus has been to provide higher quality of milk, fruits, vegetable, and that becomes a focus area from a business model perspective. So I will give you one example. Let's say 1,000-liter milk cooler with a diesel generator would cost about 4 or 5 lakh rupees. Our 1,000-liter milk cooler with energy storage cost about 7 lakh rupees. Now, and this quantum of capex is generating revenue of 3 crore in a year. So we are talking about lot of milk, right? Lot of revenues. And now, if the quality of milk goes up by only 10%, your payback happens only in few months. So that is the focus area where we develop our technologies or develop these products. So which is catering like ISO standard milk cooler designed by European world is cools milk in 3 hours. But our milk coolers are cooling milk only in 2 hours. And which means, right, 10-20% higher milk quality. So these are the kind of business models, right, which we look into, where not only our clientele gets a higher quality of produce, and it also a lot of diesel saving.
Yeah. Thank you, Nitin.
Thanks.
Yeah, Professor Dibakar, I have a question for you. This is a quite technical question. So while it is relatively easy to convert electricity to heat, the critical challenge for thermal energy storage is the significant efficiency drop when converting heat back to electricity. What is your take on this?
So actually the talk was speaking all about this. Like if we want to have a economical or more efficient conversion of like electricity back to heat, then we have to work at a higher temperature so that the quality of energy is intact or maintained, what we have already done by processing the low grade energy to high grade energy. You work at a high temperature and store it at high temperature, and then again harness it to whatever way you want to utilize it. Of course, it is challenging because if I'm speaking about working at a high temperature, say 500 plus and up to going to 1000 degrees centigrade, there will be a lot of limitations in terms of material aspect and in terms of coming up with various heat loss, thermal losses, which will be there. But if we can some way or the other maintain that type of scenario, then definitely it is a win-win situation. And I have shown some of the technology, some of the examples where this heat to electricity and back from electricity to heat at such a high temperature has been exemplified. So it is possible. It's not that it is.
Yeah. Mr. Ankit, there is a question related to industrial waste heat recovery for heating and cooling purposes. Can you give us some description about their applications with respect to a sector as an example?
Yeah. So I think, put it in very simple terms, industrial waste heat recovery is essentially about capturing heat at high temperatures and using it where it is required in low temperatures. And we have commercially worked on some of these industrial waste heat recovery applications, and I can share a couple of examples. One of them being in the ship or in the shipping line, where a lot of heat is generated, and these heat is being captured in a buffer vessel, which has a lot of these phase change materials encapsulated in a stainless steel encapsulation. This is a phase change material at somewhere between 60 to 80 degrees Celsius. So you capture this waste heat in these phase change materials, and then this heat is used for heating rooms or for heating water within that ship itself. However, there is one restriction with these waste heat recovery is that you cannot have this heat being transported over long distances, because then the losses are way too much. I think the only one of the applications that I've come across is wherein the longest I've seen is wherein this waste heat has been transported about 35 kilometers to distillation towers. And there are various other applications. I think we're working with one of the automobile companies wherein this heat being generated by the internal combustion engine in cars is being used for, especially in cold countries, for warming the cabin or for warming or for cold starting in extreme winter conditions. So, but I think still the industrial waste heat recovery, a lot of commercial applications have not happened. It exists in concept. I mean, temperatures can go from as low as 60 degrees Celsius to 300 degrees Celsius. A lot of applications, a lot of concept paper, research papers have been published, but some pilots have been done, but I think more and more pilots need to be done to prove these concepts on a commercial scale.
Yeah.
Some of them we have been involved in and they have been successful, but I think it's still far away from a large scale adoption.
Yeah, thanks, Ankit. So I think due to the paucity of time, we'll move on to the question and answer session. My teammate Kajal will take over, and thank you panelists for a very informative discussion over thermal energy storage. Thank you very much. Over to you, Kajal.
Thank you, Gautami, and thank you all the panelists for giving so much of insight on the thermal energy storage system. I think this was really helpful, and we can actually see this coming from the question and answers from all the participants. There are like a barrage of questions that has come throughout these discussions. We will just close, but I just wanted to, because there are a lot of good questions that have come. So I thought I'll just pick up a couple of them and see if the panelists want to take this up. I know that you have also answered them, but just for the, for the others to also get to know about this, and they will also be helpful for the other participants. I'm just picking up one question, which is like, how does the thermal energy storage, when we compare it with the battery storage, which is quite a common thing that, in right now that we do. So in the large scale application, how is that more useful? Especially when we are looking at the grid application, and what is the different sizes at which we can go. So I see that Ankit and Nitin, you have already done the responses, but would you like to also share it for the other participant?
Nitin, you want to go first?
Yes, so I'm not too much aware of thermal energy storage being used from heat to electricity application. But definitely there are a lot of installations of thermal energy storage where electricity is stored in form of cooling for cooling applications. In Burj Khalifa, Taipei 101, Bank of America Tower, Stanford University. All of these are very nice examples where thermal energy storage has been is deployed, right? For I think for running for past 20 years. In fact, I think GIPS city in Gurgaon also has a district cooling which is based on thermal energy storage. So these are the large grid-based thermal energy storage which are in commercial.
Ankit, do you want to add?
Yeah, so I think I had answered that question, but in short, what I think is it's really dependent on the end application. If you're talking about heating or cooling, always thermal energy storage will be far more efficient. If I'm aware about conversion of heat to electricity. In fact, we met a couple of companies in Australia who are doing these applications, wherein you can use heat, the excess heat to convert into electricity, but again, it has to be proven at the commercial scale. But just very simply put, in terms of comparison, if you're talking about heating or cooling, the thermal storage will always be far more efficient than battery storage. It'll always be far more efficient, and I don't need to explain it. I think it's common sense, because you're just storing heat and then using that instead of first storing electricity and then converting it again back to cooling or heating. So there will be a lot of losses. So it's always more efficient.
No, I absolutely agree on those points. And yes, as you rightly mentioned, we also have to look at the efficiency, not just looking at the practical solutions to it. And then only we need to look at the various application where we can use the DES. There are a few more questions which are coming, but I'm afraid that we have overpassed the time. Would you like to just answer them during the in the Q&A sessions, which is there in the Zoom section there, so that we can just try to close this session? And if there are any questions which are remaining unanswered, we will try to get them answered through, we'll capture most of these Q&A documented in a form, and we'll respond to you individually. So you can just drop in your questions and you can drop in your email IDs and we can always respond back. So thank you so much for tuning in today for this webinar, and we look forward for this interactive session and similar kind of session. And thank you so much to all our panelists for giving us so much of insightful discussion on the thermal energy storage. It was very helpful for us also, and I equally feel this will be very helpful for our participants. And we will definitely try to keep you all posted. This recording is already live recorded, so you will find the link on the YouTube, and whenever you want to go back, you can go back and listen to this again. Just before we close it, I'll request all the participants, all the panelists to switch on their videos so that we can just take one photograph of all the panelists. Zafar, are you still there? And if possible, can you switch on your video just for a minute or so? I think he's a bit away. Yeah, thanks for sharing the YouTube link, Ahona. So all the participants can also look at the YouTube link and can go back and listen to some of these conversations again, because there was a lot to absorb, and I'm sure that this will be very overwhelming for the participants. So yeah, thanks a lot, Ahona. Ahona, are you done with the screenshot?
Just give me 1 minute. I'll just take an extra one.
Switch on your video also.
Done.
Thank you so much. Thank you, everyone. Thanks for joining today. Thanks, Gautami. Thanks, Dylan.
Thank you. Thank you.
Thanks, everyone.
Thank you.
Thanks. Bye.
Bye. Bye.